There's a classic physics problem that involves a ladder leaned up against a building. So I'll put my building over here, and the ladder is at some angle, I don't know, some angle on the building. Let's say it hits right there. Guess I need my building a little bit taller. Okay, so the one that I'm inspired by is on page 317, but you'll see these problems all over the place. The idea is that there's a zombie on the ladder. What do we need? Oh shoot, unfortunately, zombies are red-ish. We can make it a grayish-black zombie here. And it's shouting for brains, but it's exerting a force on the ladder, and that force is exerting a torque. And I guess I'll just kind of lay out some of the details of the problem. An 85 kilogram zombie stands on a lightweight ladder. That means we get to disregard the mass of the ladder. That's handy. Otherwise, we'd have an additional force on the ladder. But the ladder is very light. The floor is rough, so it exerts two forces, a normal force, which we'll call F1, and a frictional force, which we'll call F2. So let's identify this point as the source of the forces from the floor, and the normal force is here, and the frictional force is, well, which way would the frictional force be? From the floor onto the ladder, I guess it's going to be that way. That is the force of static friction right there. And they want to call them F1 and F2 and F3. Oh, that's kind of silly. Let's label them as the normal force and the static frictional force. And we could call this force over here, the ladder is being pushed away from the wall. There's no friction up here though. This force is going to be the normal force from the wall. This will be the normal force from the floor. Okay, good. So we've got all of these forces labeled. There's one more force in the system, and that's the weight of the zombie itself. We'll draw that purple. Okay, so we've got M of the zombie times baby G, but because we've only got one mass in the problem, we don't have to be any more careful than that. The other thing that we're told is that the ladder hits the wall at 3.8 meters up. That's 3.8 meters above the ground. And we also know the distance between, see, when they give you these problems, they're going to give you all kinds of different options for what numbers they can tell you. This is the distance horizontally between where the ladder hits the ground and where the zombie is actually standing on the ladder looking for brains, 0.70 meters right there. So here's what I'm going to do. I'm going to actually label these distances. This one I think I'll call B, and this one I'll call A, so we don't have to worry with any actual numbers. And we can, oh, hang on just one second. Press the button for the amplifier. There's an amplifier in front of you. It's the black box. Down, 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 down. Press it. Turned off. Okay. Then what we want to do is set up some X and Y axes, like that, and we want to, well, we want to apply all of our equations. Let's find the three forces that are not given. The force of static friction, the normal force from the floor, and the normal force from the wall. And we're given this force right here. So, the three equations that we have are torque, and we have balance of forces in X, and we have balance of forces in Y. I would suggest, looking at this problem, we look at torque first, because the wonderful thing about solving for the torque is if we choose this as our axis of rotation, then we won't get a torque from the force of static friction, and we won't get a torque from the normal force from the floor at all, because that is our axis of rotation. So neither of these cause a torque about that axis of rotation. So let's choose the axis of rotation. Step one. Choose axis at base. Okay, and then net torque equals 0. And our equation that we'll get from step one will look like this. The net torque equals 0. So there is a torque from the weight of the zombie, and that torque tends to cause, about this point, that torque tends to cause a clockwise rotation, so it's negative. We're going to write negative m times g times the distance b. That's the distance, the normal distance that force acts away from the axis of rotation. And then there's another torque caused by this force right here. And then that's going to be a counterclockwise rotation, so we'll add it. That is plus the normal force from the wall. And we need the distance that acts normal to the force. It's that direction. And so this is A. All right, and that equals 0. This is a trivial equation to solve, so we'll put a little implies symbol right there, and we can write that the normal force from the wall is mgb divided by A. Cool, cool. So we can declare that done, and you guys can get some numbers for that, but I'm not interested in that kind of level of detail. The next step is, well, what do you want to do? You want to solve forces in X or you want to solve forces in Y? It actually doesn't matter. We're going to be fine either way. Let's say that we solve forces in X first. This is Newton's second law in the X direction. We're going to say the net force in the X direction is equal to 0. So we get, as we make this sucker concrete, the forces in the X direction are the force of static friction. And this is a negative force. This is negative the force from the wall, the normal force from the wall, and that stuff equals 0. So we can say, oh shoot, the static force of friction is equal to the normal force from the wall, which is in turn equal to mgb divided by A. So we can declare that also done. Check. And you have that number already, right? Yeah, so you can put that down there. Step 3. We're going to say add up all the forces in the y direction and they will equal 0. And we've got, let's see, this force is in the y direction. We've got the normal force from the floor in the positive y direction. And we've got the weight of the guy, normal force on the floor, and the weight from the guy. Weight from the guy is in the negative y direction, so we're going to say mg, that zombie, is 0. So this gives us that the normal force from the floor is m times g. This is a pretty simple problem once we got through that mess. And that is it. Now, what if we were to ask when the ladder might slip? We could even find the mu. We could be given a corollary problem that says find smallest mu s, so that the zombie can actually stand there without it slipping. Interesting. How are we going to do that? You got a mu s equation? You say mu s equals, and if it's just barely slipping, this is going to be Fs max. It's going to be Fs max divided by the normal force. So we can plug in the things that we know. Fs max. Well, Fs max is just mgb divided by A, and then we have to divide this by the normal force, which is just mg. Oh, what fun. It's B over A. The end. Center of mass and balance. This is a very simple section. The center of mass is the point about which an object won't rotate. Let's see, won't rotate because of gravity. It is certainly possible for an object to rotate about its center of mass, and that's a standard thing that happens, but it won't begin to rotate about its center of mass because of the force of gravity. So I have this strange device right here that's used for measuring distances when you're rolling across a field, and I can find the center of mass by sliding my fingers like this and balancing it, and I'm finding that the center of mass is about right here, and that's the point at which it's balanced. But I want you to notice, as I hold this sucker up like this, is half the mass on one side and half the mass on the other side? We've talked about this in class. I hope you will agree that that's not the case. That there is substantially more mass over here, but this mass over here has a very large torque because it's so far out. So more mass here, less mass over there, and that's okay. And I guess I'll just kind of lay out some of the details of the problem. An 85 kilogram zombie stands on a lightweight ladder. That means we get to disregard the mass of the ladder. That's handy. Other zombies are red-ish. We can make it a grayish-black zombie here. And it's shouting for brains, but it's exerting a force on the ladder, and that force is exerting a torque. There's a classic physics problem that involves a ladder leaned up against a building. So I'll put my building over here, and the ladder is at some angle, I don't know, some angle on the building. Let's say it hits right there. Guess I need my building a little bit taller. Okay, so the one that I'm inspired by is on page 317, but you'll see these problems all over the place. The idea is that there's a zombie on the ladder. What do we need? Oh shoot, unfortunately. Otherwise we'd have an additional force on the ladder, but the ladder is very light. The floor is rough, so it exerts two forces, a normal force, which we'll call F1, and a frictional force, which we'll call F2. So let's identify this point as the source of the forces